Analysis of single phase diode bridge rectifier with and without filter by using MATLAB-SIMULINK. This is called circuit diagram of a single phase diode bridge rectifier. In this single phase diode bridge rectifier, 4 diodes are connected like this bridge. Okay. And this is called load. And the diode D1, D2, and D3, D4. The indication is like this. And this is called our AC voltage source. We will get here the output is called DC voltage across the load for resistive load. And the current when positive off cycle, the positive for positive off cycle, diode D1 and D2 are forward biased. D1 and D2 are forward biased because of this current entering like this, the current circulating to the load in this way. This is the current. Current entering into the resistive load is here positive and negative. The output voltage V0 here, positive and negative. This is called positive off cycle. For positive off cycle, diode D1, D2 are conducting. Means forward bias means automatically it is conducting. Diode is an uncontrolled device. That's why when it is forward bias, it is automatically is conduct and is turned on, and then the current flowing to the load is called like this. The next for a negative off cycle, this diode D3 and D4 are forward biased, and this current in this load is called in this direction. Okay, this is called direction of the current. For negative off cycle, diode D3, D4 are conducting. Here diode D3 is conducting. This is called current direction. Okay, this is called current direction. In this way, the current is circulating. This is for negative off cycle. For positive off cycle, diode D1, D2 are conducting. In this way, this current is circulating into the load. Current flow into the load. Okay, this is called for positive off cycle D1, D2. For negative off cycle D3, D4 are conducting. Okay, that means the voltage across the load is always positive. Resistive load is always positive. Here positive and negative present. The next, these are the waveforms of single phase diode bridge rectifier. This is our supply voltage Vs. Okay, 0 to pi, pi to 2 pi, 2 to 3 pi, 0 to pi, positive off cycle, pi to 2 pi, negative off cycle, 2 pi to 3 pi, positive off cycle. Like this, our input AC voltage changes. Then average output voltage, the output voltage across the load, resistive load, in this like this red color, this way, we will get positive only. The average output voltage is positive only across the load. Across the load here, this is called V0. For negative off cycle and positive off cycle, the current entering into the load here positive and negative. This is the direction only. Okay, the current entering in this direction. For negative off cycle, for positive off cycle, the current direction is same to the load. That's why the output voltage is always positive. This is called positive. For D1, D2 are conducting, the output positive output voltage present across the load. This is called Vm. For negative off cycle, D3, D4 are conducting. D3, D4 are conducting because of this positive output voltage present across the load. Like this. For another positive off cycle, D1, D2. For positive off cycle, D1, D2 are conducting. For negative off cycle, D3, D4 are conducting. So that's why we will get this is called full wave rectifier, single phase full wave diode bridge rectifier. And the next, what is the voltage across the diode D1 and D2? When diode D1, D2 are turned on, that means when it is on, means it like a short circuit. There's like a closed switch. That means under closed condition, under on condition, the voltage drop across the diode is equal to 0. That's why VD1, VD2 voltage when D1, D2 are turned on is equal to 0. When D1, D2 are turned on means the voltage across the diode D1, D2 is equal to 0. If D1, D2, D3, D4 are turned on, that is called this D3, D4 are forward biased, means remaining two diodes are reverse biased. So because of negative voltage, that voltage is present across the diode D1 and D2. VM. This is called peak inverse voltage. For bridge rectifier, peak inverse voltage is called VM. Okay. For positive half cycle, D1, D2 are conducting. So conducting means on. For on, diode voltage drop 0 ideally. Okay. So voltage drop across the diode is equal to 0 when two diodes are turned on. Then D1, D2 are turned off here. That's why we will get this voltage, supply voltage. The supply voltage present across the diodes, that is called minus VM. Then again for next half cycle, 2 pi to 3 pi, diode D1, D2 are forward biased. That's why diode voltage drop across the diodes are 0. So this is the voltage VD1, VD2. So next VD3, VD4. When D1, D2 are forward biased means D3, D4 are reverse biased. D1, D2 are conducting means D3, D4 are not conducting. That is called, it's like open circuit. That's why negative negative voltage present across these devices D3, D4. Next here D3, D4 are conducting. That's why the voltage is 0. Here D1, D2 are conducting means D3, D4 are not conducting, like opposite. That's why the voltage is present. Okay. Next current ID1, ID2. So ID1, ID2, then when two diodes are turned on, then only the current is flowing to the diode. So where conducting means 0 to pi, diode D1, D2 are conducting. That's why the current flowing to the diode D1, D2 increases like this. IM is equal to VM by R. Current flowing to the diode is called VM by R. Like this. In this year, the diode D1, this duration pi to 2 pi. Diode D1, D2 are not conducting, like open circuit. That's why current is equal to 0. And again diode D1, D2, 2 pi to 3 pi is conducting. That's why current is nothing but VM by R. So like this is the waveform of current flowing to the diode D1 and D2. Okay. Next source current. Source current is called VM by R. Source current IS is equal to VM by R. This is called VM by R. It changes like this. It's follow the same as source voltage, but magnitude is different. IS is equal to VM by R. Like this, these are the waveforms of single phase diode bridge rectifier. We can understand by using MATLAB-SIMULINK. By simulating the circuit single phase diode bridge rectifier, we can understand the waveforms. And then coming to the average value of diode current. Average value of diode current is nothing but 1 by 2 pi integration 0 to 2 pi Im sin omega t. Then we will get Im by pi for differentiating. Integration. Then we will get Im by pi. Im by pi is called average value of diode current. Then RMS value of diode current is called Im by 2 by simplifying like this. So RMS value of diode current is called y your limits 0 to pi and 1 by 2 pi means for a duration of 0 to 2 pi, diode is conducting 0 to pi only. Total duration is called 0 to 2 pi. Diode is conducting 0 to pi. That's why, so we will take limits for total duration is called 1 by 2 pi. In this duration, the diode is conducting 0 to pi only. That's why we will get like this. 1 by 2 pi integration 0 to pi. I square, Im square, sin square omega t. This is called RMS value. RMS value of diode current. That is equal to Im by 2. Then peak repetitive diode current is called Im is equal to Vm by R. Next, coming to the RMS value of line, RMS value of voltage is called, so RMS value of output voltage. So why this 0 to pi and 1 by pi means the waveform is symmetrical for 0 to pi and to pi to 2 pi like this. The waveform is repeating. That's why for half cycle is required to find the RMS value. So here 0 to pi is called total time duration and is changing from 0 to pi. Again, same cycle repeating. That's why no need to take from the year pi onwards. So only 0 to pi is required. So that's why. So RMS value is called 1 by pi integration 0 to pi Vm sin omega t whole square into d omega t. That is called square root. So then we will get by simplifying Vm by root 2, that is equal to 0.707 times of Vm. This is called RMS value. RMS value is equal to Vm by root 2. And then RMS value of line current is called IL is equal to VRMS by R. IRMS is equal to VRMS by R. VRMS is called 0.707 times of Vm. That is equal to 0.707 times Vm by R. So like this, these are the different types of formulas related to the single phase diode bridge rectifier. Then this can be understood by using MATLAB-SIMULINK with filter and without filter. By using filter, what is the output voltage waveform changes? Without filter, we will get like this waveform. Okay, output voltage. With filter, these ripples are reduces and we will get almost constant DC voltage with filter. Okay. Open MATLAB-SIMULINK. Here, take first AC voltage source. AC voltage source. This is the input of our bridge rectifier. This is called AC voltage source. Place here. Then next take diode. Diode. Don't take this type of diode. And diode. Okay. So take this diode. Press Ctrl R and rotate like this. This is called diode. And by using mouse right click, drag like this. Place here. Similarly, one more diode. Like this. Connect the diodes in this way. This is called diode connection, bridge rectifier connection. Connect positive terminal of AC voltage source to the one pole of this diode bridge rectifier. And negative connect here, another pole of diode bridge rectifier. This is called bridge rectifier connection. And take one series RLC branch. Series RLC branch. So from this, select only resistor. First, we have to considering on resistor, resistive load, diode bridge rectifier, the resistive load, apply, then OK, and rotate, place here, connect this way. Like this is the diode connection, load connection. And here, to measure the voltage across the load, take one voltage measurement. Voltage measurement. Like this. Connect this voltage measurement exactly parallel to the resistive load. This way. Okay. This is called voltage across the load. And also similarly, if you want to measure the supply voltage, take one similar way, take this is called voltage measurement. Place here voltage measurement and connect one terminal in this direction, other terminal. This is called voltage source voltage. Source voltage is over and load voltage is over. And next, if you want to measure the voltage across the diode, and select like this. Connect, this is called voltage across the diode. This way, connect this way. This is called diode voltage, diode D1. And also for positive half cycle, these two diodes are conducting, this diode and this diode. For positive half cycle, these two diodes, the diode D1 and D2 are conducting. This diode and this diode, positive half cycle. That's why the voltage across the two diodes waveform is same. So no need to measure the voltage waveform across this diode because of same voltage. D1, D2, we will get same type of voltage waveform. But this waveform is different. That's why select one voltage marker, voltage measurement, connect this voltage measurement across this diode. Like this, okay? So how many ports required in scope? First one, source voltage, diode voltages, and load voltages. That is called 1, 2, 3, 4. 4 ports are required in scope. Select scope and change input ports is equal to 4. Number of ports are nothing but 4. Like this, change the number of input ports is equal to 4. Apply, then okay. Okay, this is called scope for voltage measurement. And copy like this for current. Okay. Select one current measurement and connect across the source current measurement. To measure the current measurement. Remove this current terminal. Can I place here? This is called source current. Next, diode current. Diode current. This for current flowing into this diode D1 and D2 are both are same when it is forward biased. That's why take one current measurement and place here. Current measurement. This is called current flowing into this diode. Okay, in this way we have to measure. This one. Next, current flowing to the load also. So we required one more current measurement. Current flowing to the load. Connect in this way. This is called current flowing to the load. And next, so source current, diode current, and load current. Current flowing to this diode. And also similarly, find the current flowing to this diode also. Okay. So that's why I'm connecting one current measurement in series with the source. Press controller. Connect one terminal here, other terminal here. This is called current measurement. Current measurement and voltage measurements connection is over. Meters are connected. First, connect voltage measurements terminals. First, I'm choosing source voltage. Source voltage. Okay. This is called source side parameters. First one, this is called source voltage. Next, diode voltage, D1. Next, another diode, D2. And then finally, diode voltage, and then finally, voltage across the load. Okay. The next, this is called source connection. Source voltage sources are connection is over. The next current measurement. First one is called current measurement, source current. Second one is called diode current. This diode current. Okay, diode current. Next one, another diode current. Where is that here? Next, finally, current flow into the load. Like this, connect all sources to the scope. Okay. Next, change source voltage. For example, peak amplitude is called, for example, 20 volts. Frequency 50 Hz. Then apply, and okay. Frequency 50 Hz. Then similar, what is the load resistance? 10 ohms, for example. Okay, then simulate. Before going to the simulation, take one power guy because of this error, because of power guy. Power guy, place here. Source voltage is called 50 Hz, that's why time is called 20 milliseconds. 0.02 is called 1 cycle. One complete cycle is called 0.02. So right here, for example, 0.1 to get more than 1 cycle, and press simulate and run. Okay, then we will get this is called voltage waveforms. Voltage. So change sample time is equal to 0.001001. Then apply. Okay, and this simulate again. Then open scope. The separate how many terminals here? 4 ports. That's why go to layout and change to 4. This is our output voltage waveforms. Go to style, change background color white. Here also white. Axis color black. And thickness is called 2. And color is called red. Then apply. Okay. So this is called our source voltage waveform. Similar way, change the remaining waveforms, colors, background white, and active display 2. Right here, select 2 thickness and color, another color, pink color, then apply. Then active display 3, change like 3 and take another color, then apply, then okay. Okay. And also similar way for active display 4. For active display, go to style 4, change the thickness, change color also. Okay, the thickness like this. Then apply. Okay. This is called our output voltage waveforms. Source voltage waveform. This is a source voltage waveform. Okay. And then this is called diode D1, voltage across the diode D1, and it also diode D2. Voltage across this diode D1 and D2 are called, this is the voltage waveform. This is the voltage across the diode D1 and D2. Diode D1 and D2. The diode. So D1, D2 are conducting at for positive half cycle. Okay. So that's why you will get like this. The next another half cycles you will get like this. So when D1, D2 are conducting, D2, D3, D4 are non-conducting. Here D1, D2 are not conducting, D3, D4 are conducting. Like this. So when two diodes are conducting, another 2 diodes are off. Okay. This is called voltage across the diode D1. If diode D1, D2 are conducting here, that's why there's short circuit, like a zero voltage present. Diode D1, D2 are off, means the diode D3, D4 are conducting, that's why here zero voltage. Then next, finally, the output voltage. For positive half cycle, D1, D2 are conducting, we will get this type of output voltage. For negative half cycle, D3, D4 are conducting. So that's why the voltage across the D3, D4 is equal to 0. And then the voltage across the D3, D4 is nothing but, that is load voltage is nothing but positive voltage, that is called this. So and when D1, D2 are conducting, diode voltage across the diode D1, D2 is equal to 0. And D2, D3, D4, another these two diodes are reverse bias. That's why voltage is present. And then because of this conduction, diode D1, D2, and then we will get the positive output voltage. When D3, D4 are conducting, this voltage is equal to 0, and then D1, D2 voltage is called supply voltage. Okay, the voltage across the diodes is supply voltage. And also because of D3, D4, the current flowing to the resistor is nothing but positive half cycle. So like this. So like this, the voltage positive of the full wave rectifier voltage we will get across the load. Okay, this is about voltage waveforms. Then coming to the current waveforms. Current waveforms. Open this current scope and press here. Separate the they press vertical, and then so we will get like this. And here change the layout style. Go to style, change background color white, and here also white. Axis color is color. In this way we have to change active display 1, and here thickness change like this, and the color red, then apply. Okay, then one by one change the remaining colors also, then it is can be visible. Nice. Then the second one, active display 2, and change thickness and also color, apply. Then next active display 3, then change the color and thickness, next color, and then apply. Active display 4, okay, then thickness, and then apply another color, apply, then okay. This is called current flow into the diodes. Current flow into the current fed by the source. First one is called source current. Like this, source current is changes. First one is called source current, and the next one source current, and the next one, what is the current? Diode current. For positive half cycle, diode D1, D2 are conducting. That's why current flow into the D1, D2 is nothing but when two diodes are turned on, we will get current like this. When two D1, D2 are here turned off, that's why zero current. Here D1, D2 are turned on, that's why positive cycle, positive half cycle voltage current get like this. When D1, D2 are turned off, the current is equal to 0. When here D1, D2 are again turned on, then we will get like this. When D1, D2 are turned on, D3, D4 are turned off. When two diodes are conducting, another two diodes are not conducting. That's why if D1, D2 are conducting here, we will get current, and the D3, D4 are not conducting off. That's why we will get zero current. And then here D1, D2 are not conducting, means D3, D4 are conducting. That's why we will get this type of current. Okay. Then finally, so we will get a current flow into the load in this way, changes like this. This is called current flow into the load. What is the current across the load is nothing but Im is equal to Vm by R. Vm by R is nothing but Vm is equal to here 20. 20 divided by resistance R is called 10. So 20 divided by 10 is called 2. So that's why we will get like this. This is the voltage. Peak voltage. What is our peak voltage? 20. What is our resistance? 10. That is called Im is equal to Vm by R. Pass to peak. Vm by this is called Vm by R. 20 divided by 10. That's a 2. Like this, we will get voltages and current waveforms of single phase diode bridge rectifier. Then coming to the what is the RMS value of load? What is the RMS value of voltage across the load? So to find this, we need one RMS block. RMS. Place RMS here. Okay. Take another type of RMS. Here, what is the source voltage here? Frequency 50 Hz. That's why. So we want to change the frequency. Open this and here right here 50 Hz. And initial 0. Then apply. Okay. This is used to measure the RMS value of voltage. The last one is called voltage across the load. That's why connect here this terminal. Then next take one, what is that? Display. Take display, place here and connect like this. The display used to measure the what is this? To display the RMS value of source voltage. Similar way, find the RMS value of source current. So this is called RMS. So last one is called RMS value of current. That's why copy this, paste here. Last one, this is called our last one. Is called load current, and this is called RMS, same 50 Hz and display, and then simulate again. This is called VRMS is equal to Vm by root 2, 20 by root 2. Okay, so we will get like this 12.72. Okay, this is called voltage across the load, RMS value of voltage across the load. And then second one, current. Im is equal to Vm by R. Here 20 voltage and a 10 ohm resistance. That's why 20 by 10 is called 2. 20 by the load current is called Im by 2. So what is the load current here? IL is equal to, so Vm by root 2 by R. Vm by root 2 into R. That is 0.707 into Vm by R. So voltage here 1.272. This is called Vm. Okay. So Vm by R. Vm is called 12.72 by 10. What is the resistance? 10. So 12.72 by 10 is called 1.272. That is called current flow into the load. So in this way, we can understand the RMS value of load voltage and RMS value of current flow into the load. This is called without filter. So without filter, we are getting this voltage type of voltage waveforms. Okay, this type of voltage waveform because of without filters. If one capacitor is connected parallel to the load, that is called with filter. So take one series RLC branch. Under this, change this into C, then apply. This is called 1 microfarad. For example, if it is capacitor is called 1 microfarad, what is the output voltage waveform? With filter. Connect exactly parallel to the load and then simulate. Then what is the variations in output voltage we can observe? Okay, by changing the capacitance like this. Again, change this. For example, the load resistor is called 100 ohms, and your capacitance same as it is, and changing the load resistance. This is under one of the important concepts that is called design of filters. It comes under design of filters, but here I'm randomly by changing the values of resistance and capacitance. So what is the output voltage I'm checking? Again, I'm changing the capacitance to millifarads instead of microfarads, I'm changing the 1 millifarads. Then again, I'm simulating, and then I'm checking the voltage waveform. So like this is called our with filter. The voltage waveform is changes. The ripples are reducing. The ripples changes like this. This is because of this kept filter. Okay. Because of the filter, the ripples in the output voltage can be reduced. So this is called with single phase diode bridge rectifier with filter. Okay. And also this is about with filter for load of 100 ohms, capacitance of 1 millifarads. Okay. Then we will get the ripples are reducing. Okay. This is about a single phase diode bridge rectifier with filter, and then current waveforms are changing like this also. The current, this is called load current. Current flowing to the load is also changes. The ripples also reducing in the current waveform. Okay. This is about a single phase diode bridge rectifier with and without filter.